Hi, this is the third installment of this four-part series of looking at a few of the problems seen in your online tut tests. So this one deals with tut3. Let's look at some questions. Okay, so this was, I think, the first question in the online tut. You are given a joint distribution for gender and outcomes on some course, I believe. Gender is split between female and male. Perhaps a more precise designation of this dichotomy should have been sex rather than gender. Anyway, let's just go with it for now. So we've got male and female, and on the outcome we've got pass and fail. Okay. So X is outcome on the course, whether you passed or failed, whether a given person passed or failed, and Y is the sex of a given individual who took the course, whether they are male or female. Okay. Question 1 asks, are X and Y independent? Okay, so this is a simple question, but requires a little bit of work, because we know that independence is given by the following rule or definition. We have a joint distribution of X and Y if that equals the product of the marginal distributions, then we know that X and Y are independent. Okay, so all we have to do is check whether this statement holds in this case over here. That's the joint distribution. Okay, so remember, we have to find, it has to be true, this has to be true for all values of the joint probability of X and Y and their respective marginal probabilities. Okay, so how do we start in approaching this question? First thing we have to do is find these things, right? This is given to us, but the marginal probability distributions are not given to us. So the first order of business is to find these marginal densities. Okay, so let's do that. Let's start with Y. So the marginal density of Y is given, let's get rid of this board over here. Marginal density of Y is given by the sum of all values for each of its possible outcomes over X. So we have to, for female, we have to sum over pass and fail, right? So that's 0.37 plus 0.17, and that results in 0.54. So that's the marginal probability of someone in this course being female. Now we need to find the marginal probability of an individual being male, and that of course is just given by 0.46. Perhaps I should just write down the definition for marginal probability. So given joint distribution, I'll just write here JD for joint distribution, f of xy, marginal distribution is given by the sum marginal distribution of x, or f of x, is given by sum over y of fx y. Okay, so we found the marginal distribution of y. We summed over x. Now we need to find the marginal distribution of x, sum f of x over y. So here for pass, we've got 0.37 plus 0.29, which equals 0.66. And for fail, we've got 0.17 plus 0.17, which equals 0.34. Now we can proceed to answer the question, right? Which is whether this statement holds in this case. In other words, we are asking, is it the case that 0.37 equals the product of 0.54 and 0.66? Also, we are asking whether it is the case that 0.29 equals the product of 0.46 and 0.66. We are also asking whether it is the case that 0.17 equals the product of 0.54 and 0.34. And lastly, we are asking whether it is the case that 0.17 equals the product 0.46 and 0.34. In fact, what we are asking is that all of these equalities are true. If that is the case, then x and y are independent. Whether you are male or female has no bearing on whether you pass or fail this course. Okay, that's the claim that we're making when we state that. Okay, let's find out if it's true. Well, all we have to do is take these products and then see whether these equalities in fact make sense. But we don't even need to do that, because if we just look at these last two equalities over here, both of these things can't be true. Can't be true that 0.17 equals 0.54 times 0.34 and 0.17 equals 0.46 times 0.34. So therefore, we immediately know that these are not independent, because, again, this statement, f of xy equals the product of f of x and f of y, does not hold in all instances. And the answer here is therefore no. X and y are not independent. Okay, here's another question at the bottom. The probability that a student passes the course given that she is female is okay, what is the probability that a student passes the course given that she is female? Okay, so immediately we notice that this is a conditional probability question, right? Because of this word given. When we see the word given or the word if, in other words, whenever you see that a claim has some condition, you know you're dealing with a conditional probability. The definition of the conditional probability of some variable given some other variable looks like this. In this case, we're looking at the probability that a student passes the course given that she's female. So we are conditioning on sex in this case, gender. So what you have here is f of x given y equals joint distribution of x and y divided by f of y. Okay, so now it's just a matter of plugging values into this little relation. Okay, so let's do that. Equals the joint distribution that a student passes the course and is female is just looked up on this table, and it's given by 0.37, passed the course and is female. So numerator in this ratio is 0.37, and the denominator, here we need the marginal distribution f of y equals female, right? Question relates to females in this case, but we don't have to calculate this. We've already done that in an earlier step. So we know that the value there is 0.54, and that should give you the answer. Okay, let's move on. This question might have had a few heads scratching. Okay, if the probability of A union B equals the probability of A plus the probability of B minus the probability of the intersection of A and B, then the probability of the union of A, B, and C is, okay, so here the hint says to draw a Venn diagram with 3 overlapping sets to determine the solution. Let's just go through the first case where you have just A and B. So let's say you have 2 sets of elements that overlap. The union of those 2 sets is given by the total area effectively covered by them, or at least all of the elements contained in both of those sets. Now, one thing to remember when you add, so when you add A and B, you're adding this entire set here and that entire set there. In other words, this area in the middle is being accounted for twice. And that's why you have this minus over here. Okay. Now, when you have 3 sets, it's a little bit more convoluted. So here's set 1, set 2, set 3. Now you start out in the same way that you did with the case where there's only 2 sets. That is, you add all 3 of them, right? You want to get the elements, the union of the elements in all 3 sets. But starting pairwise, you notice that you have to subtract these areas over there, for instance, and that area over there, and that area over there, just like you did in the case when you have two overlapping sets. So you have to do the subtraction pairwise. In other words, you have to subtract for each pair of sets. But notice what happens when you do that. So when you, let's call this set A, and this one set B, and this one set C. When you subtract the intersection of A and B over here, yes, Faye? When you subtract the intersection of A and B, which will be that part over there, once, that's great. You need to get rid of that. And when you subtract then the intersection of B and C, that's also great. You need to get rid of that at least once. And then lastly, you subtract the intersection of A and C. You need to get rid of that. Okay. Now notice what has happened to this little section in the middle here. The intersection of the 3 sets. You subtracted that thrice. Which means this is now absent. This set of elements given by the intersection of the 3 sets is now completely taken out because you've subtracted that little section 3 times. So you need to add that back. In other words, you need to do this. You need to add back the intersection of A, B, and C. Okay, is A the correct answer though? Let's just go through it. It says that you take the probability of A plus B plus P of B plus P of C minus intersection of A and B minus intersection of B and C minus intersection of A and C, and then minus the intersection of C and B. Oh, that's not right. This term appears twice, right? We've just swapped the letters around. so that's not right. But we definitely want an answer that has this last term in it. So we'll just look for that one. This one has the last term in it, but it doesn't have the subtraction of the pairwise sets in them, these three. So therefore, that's also not, B is also not the correct answer. What about C? Well, C subtracts the union of A and B. Well, that's clearly not right. What about D? D looks like a plausible answer. And E looks identical to D, except that it has the negative sign. Okay. Moving on to the next question. All right, this is a fun one. In Switzerland, the life expectancy at birth is 83 years. Consider the random variable x, the age at death of a random Swiss individual. The probability distribution of x is likely to be, so if you could sample a bunch or consider the whole population of Swiss people, what will the distribution of their age at death look like? Given that the life expectancy at birth is 83 years. So this is an interesting one. So life expectancy at birth. So on average, you can expect a Swiss person to live to 83 years. So let's just draw the number line, skew as it is. So you can expect a Swiss person to live to 83 years on average, right? That's the average life expectancy, which is pretty high, but probably more or less accurate, given that it's Switzerland. Okay. Now, the question you can ask yourself is, are we likely to observe, is this likely to be a symmetric distribution? Are we likely to observe people on either side of that distribution in equal proportion? In other words, you might observe a few deaths at 0 to 1 years old, likely very few in Switzerland. But is it the case that you might observe people who are 160 years old? Right? Highly unlikely. Right? So this is probably not going to be a symmetric distribution. In fact, it's probably going to be highly skewed. And in fact, it's probably going to be highly skewed to the left. Why to the left? Because we will observe, although it's few cases, we will observe some deaths in early life, kids born with complications, etc., or just dying during childbirth, although it's rare, it might happen. We will observe those, and we will also really observe individuals who live to the age of 100 plus. So this is probably going to be a left skewed distribution. High relative average, but some skewed to the left. Okay, likely most individuals are going to live to some age beyond 80. Right, so the mode and the median will lie somewhere to the right of the mean in this case. Okay, let's move on to the next question. Two random variables, x and y, both have symmetric probability distributions with the same population mean and variance. The PDF of x is mesokurtic and the PDF of y is leptokurtic. How do these distributions differ with respect to the probabilities of observing different values of x and y respectively? So that's a little bit of a complicated question, but the important thing to note here is the distinction between mesokurtic and leptokurtic. So all that's required is to know what the definitions of those two things are. And of course here we are talking about the kurtosis of a distribution. These are measures of kurtosis or characteristics of kurtosis, mesokurtic or leptokurtic. Okay. So once you know the definitions of these two things, it's easy to answer this question. Let's consider A. X is a discrete random variable and Y is a continuous random variable. No, this kurtosis has got nothing to do with discrete versus random, at least not fundamentally. There is a higher probability of observing extreme values of X than is the case for Y. Now, we know that a leptokurtic distribution is likely going to have, let's say this is a mesokurtic distribution, standard normal distribution. Leptokurtic distribution is likely going to have a higher mass in the tails, right? Which means there's a higher likelihood of observing extreme values for a leptokurtic distribution than is the case for a mesokurtic distribution. So which one is mesokurtic? Which one is leptokurtic? X is mesokurtic, so that's X over there, and leptokurtic is Y over there. B says there's a higher probability of observing extreme values for X than is the case for Y. We just said the opposite, so that's not right. There's a lower probability of observing extreme values of Y than is the case for X, saying the exact same thing as B. There's a higher probability of observing extreme values of Y than is the case for X. That sounds better. The difference in shape doesn't influence the probabilities of observing different values. Okay, E, unlikely to be true. Okay, so that's the approach to this question. Just understanding the definition of mesokurtic and leptokurtic and realizing that in the case of leptokurtic, there's a higher likelihood of observing more extreme values than is the case in a mesokurtic distribution. Okay, next question. So this one asks, when X and Y are two independent random variables, then the covariance of X and Y is 0 because, and then a range of options are given. So to answer this question, it's just useful to remember the definition of covariance, which is given by expected value of the product of X and Y minus mu of X, product of mu of X and mu of Y. That's the definition of covariance. Okay. One of the properties of independence is that under independence, the following holds. Expected value of X times Y equals the product of the respective expected values. The respective expected values. Therefore, this becomes, under independence, E of X times E of Y minus mu X times mu Y. But we know that mu is just the symbol for the expected value of X, and mu Y is just the symbol for the expected value of Y, so this must equal 0. As simple as that. Just know the definition. Next question. If the correlation coefficient rho for two random variables X and Y is given by rho equals 0.9, it implies that. So let's just ask us what does the rho value tell us? What does it indicate? 5 options. A, the relationship between X and Y is almost deterministic. No, that's certainly not the case. B, there's a positive relationship between X and Y. Well, that's true. There's a positive 0.9. There's no negative sign. Therefore, this is certainly accurate. Let's see if it's the best answer. C, there's a strong positive relationship between X and Y. Does the rho value give us an indication of the strength of the relationship between two variables? I think it does. So this is probably also right. D, correlation is not causation. nonsense, not nonsense, but not especially applicable or an especially salient statement given the question asked. E, there is a strong relationship between x and y. Well, that's true as well. 0.9 is a high value. Remember that the row value ranges between minus 1 and plus 1. Therefore, a value of 0.9 is quite high and indicates a strong relationship between x and y. So we've got three potentially accurate statements. What is the best answer to this question? What is the best thing we can say given this value? I'll leave it for you to decide. Next question. Okay, this next question provides us with some data on weight in kilograms and height in centimeters of 10 individuals, and then asks us to do some calculations based on those data. First one is to find the mean of x, and to do this we use the standard definition of let's get this pen going. Standard definition of mean, which is the sum of xi over n. In this case, it's the sum of all these individual values divided by 10, because that's the number of values we have. Okay, and to find the mean of y, we do the same. When we do that calculation, by my lights, for x we get a mean value of 66.1, and for y we get a mean value of 172.6. Again, for x we sum all of these numbers, add them up, divide by 10. For y, add up all these numbers, divide by 10. Okay, next we have to find the variance of x. Okay, so here we use the definition of variance. So definition of variance looks like that. We have the sum of xi minus x bar all squared divided by n minus 1. So we found the value of x bar and y bar. So all we need to do is plug those means in there respectively, and then plug in the actual data of x and y. So what does that mean? In the case of x, we'll say 61 minus 66.1 squared plus 54 minus 66.1 squared, and so on and so on, until we get to our final value, which is plus 68 minus 66.1 squared. And when we do that, we get some result. We divide that by 9. So all of this gets divided by 9, which is n minus 1. The answer to that is 46.76. Let's write it over here. 46.76. Okay, we can repeat the same process for y. It's exactly the same process, just the numbers differ. And we should get a value of 60.71. And there we have found our variances. Okay. Now, of course, we can just take the square root of each of those values to find the standard deviations. The standard deviation, so S of x is equal to 6,8386, 8386, and the standard deviation of y is given by the square root of 60.71, which equals 7,7917. Okay, and we'll need those values later, which is why we calculated them. Then we need to find the covariance of x and y. Again, we just look at our definition for covariance. That's given by sum of xi minus x bar multiplied by yi minus y bar divided by n minus 1. So again, we just plug values into this formula and find our result. So let's just do one or two little steps. So this will equal 61 minus 66.1 multiplied by 172.6 minus, oops, that should be, let's get rid of that. That's the mean of y. We don't need that yet. First we need the first value of y, 161 minus 172.6. Let's just neaten this up a little bit. Here we go. So that would be the first term in this expression. Then we need to add the next one. So we've done those two values. Now we do the next pair of values plus 54 minus the mean of x again, 66.1. Multiply that by 159 minus 172.6, and so on and so on and so on. Do that for every pair of x and y in this table until we get to the very last one. And once we've done that, we should end up with the value of, well, the next step, of course, is to divide by n minus 1 again is 9, so we divide all of those by 9, and we get a value of 39.4889, rounded to 4 decimal places. So that's our covariance. So we know that x and y are positively related based on that covariance. And then the final question asks us to calculate the correlation coefficient. And of course, that definition for that is simply the covariance divided by the product of two standard deviations of x and y respectively, which we've already calculated over here. So this becomes 39.4889 divided by 6,8386 times 7,7917. And that gives us an answer of something like 0,7411. Okay. So how do we interpret this number? Correlation coefficient of 0,7411. Well, it's fairly close to 1 and it's positive, so we can say that there is a strong positive correlation between x and y. in this case. And using the actual variables that we've been given, we can say that there's a strong and positive correlation between weight in kilograms and height in centimeters. In other words, taller people on average are heavier than shorter people. Okay, next, true or false? Given that the median of x equals 67 and the median of y equals 173, and you can verify this, the distribution of the two samples drawn for x and y are highly skewed. The distributions are skewed, highly skewed, is the statement that's made there. Now, how will we assess the validity of that statement? Well, one way is to simply compare the means to the medians, because we know that in skewed distributions, the means and the medians generally are not equal. And the further apart they are, the more highly skewed the distribution. The mean of x is 66.1. The median is given as 67, so that's very close. And the mean of y is given as 172.6, and the median is given as 173.5. So they're definitely not equal. So these distributions are not perfectly symmetric. However, it would be a bit of a stretch to say that they are highly skewed. I think you might agree. Okay. Okay, on this last slide, I'll be looking at perhaps just one example from each of these questions and leave the rest for you to do as an exercise. In fact, both of these come from your practical, your practice exercises. Okay, so let's look at the first example. You are given some information about some random variable x. It follows a normal distribution with mean 69 and variance of 9. Okay, that's what that n 69, 9 indicates. Indicates that x is normally distributed with mean value 69, variance 9. Then you're asked to calculate the probability that some random x chosen from this distribution lies within the following ranges. Okay. So the first one asks you to check the probability that x lies between -infinity and 74. So how do you approach this? Okay, so as a first step, you can transform the limits in the probability to z values, or you can first split the probability and then do the transformation. Let's go with the former approach. Okay, so the transformation from random variable x, normally distributed random variable x, the way z score is given by this little relation, z equals x minus mu over sigma. Of course, all of these values are given to us, so it's just a matter of substituting. So to transform this question, which relates to the random variable x, to one which relates to a z score, we just have to apply this little formula to both limits of that thing. So let's do that. Okay, so we'll say probability that -infinity minus 69 over 3. Remember, we are given the variance of 9, therefore the standard deviation is 3. And we are transforming the x variable to a z score. So z lies between this ratio and the following ratio, 74 minus 69 over 3. You can simplify, and this stays -infinity, because -infinity minus 69 stays in minus infinity, and minus infinity divided by 3 is still minus infinity. And on the other side, the upper limit is 5 over 3. So now we can almost look this up in the Z table. First we have to break this into 2, because the Z table only gives us probabilities ranging from 0 to positive infinity. And here we have a probability problem that spans minus infinity to plus 5 over 3. If we visualize this graphically, if we make a graphical representation of this problem, this is our Z table with 0 over there, minus infinity over here, plus infinity on the other side, and 5 over 3 lying somewhere around there. We are effectively looking at determining the area, the size of the shaded area over here. But we know that the Z table only gives us the area for this half of the distribution, 0 to infinity. So we have to split this up, this problem over here. The way we do that, as we said, we split it up always at the point of 0. The probability that Z lies between minus infinity and 0 plus probability that Z lies between 0 and 5 over 3. This is identical to that. The only reason to split it up is so that we can actually look up the values in the Z table. Now this value doesn't need to be looked up. We know that this half of the distribution, the probability, or the area under the curve for that half is equal to 0.5. So now we just need to add this value over here, and that we look up in the table. So we're looking for the probability that Z lies between 0 and 5 over 3. 5 over 3 can also be written as 1,6. If we round off this to the second decimal, and we probably should round off to the second decimal since our Z table only gives us values up to 2 decimal points that we can look up probabilities for. And when we look up the probability that Z lies between 0 and 1.67, we find the following value. Giving us a final answer of 0,9525. So there's a 0.9525 probability that x, random variable x, drawn from this distribution, lies between minus infinity and 74. Okay. You follow a similar process for the next one. So in this example, again, you're going to end up with an area that straddles 0. In this case, the area, let's just get rid of this. So these shades here. In this case, the area will range from let's see. In the left limit, you'll have 68 minus 69 over 3, which equals 1 over 3. So graphically, the area you're interested in this case, is given over here. 1 over 3 minus 1 over 3 to 5 over 3. definitely not drawn to scale. So again, in this case, you're going to have to split up the probability at the point of 0. So ultimately, we'll have probability that Z lies between 1/3 and 0. Oops. Plus probability that Z lies between 0 and, in this case you've got 73, so rather than 5/3 you'll have 4/3 in the right limit. Okay, so this relates to this problem over here. And these values can now be looked up in the Z table. So for the first one, over here, you'll look up the probability that Z lies between 0 and 1/3. And over here, you look up the probability that Z lies between 0 and 4/3. And you'll sum those two values together. And it turns out that those values are 0, 1, 2, 9, 3 plus 0, 4, 0, 8, 2. And that is the probability. Once you've summed that, you'll find the probability that X lies between 68 and 73. Okay. Let's quickly get rid of all of these. So we can deal with question from the next. The next problem. Okay, in the next problem, things are done a little bit differently. So rather than looking up the probability that some random variable x lies within some range, we're interested in the probability that the mean of a sample drawn from a normally distributed random variable, from a normal distribution, lies within some range. So let's just look at the first one in this regard. The key difference between the question up here and the question over here is these words here. Find the probability that the mean value of 25 randomly chosen X observations. So here you know you're dealing with the mean of a sample drawn from some distribution. Okay, from a normal distribution. All right. What that means is that rather than use the same formula for the Z value that we did up there, we're going to use a slightly different one, because now we're dealing with a sample and we have to account for the fact that we have a sample. So Z now becomes X minus mu over sigma divided by the square root of n. All right. Now, with that bit of information, we can proceed to answer this first question. Find the probability that X bar, the mean of X, lies between 19 and 21. Okay. So again, we can immediately transform those limits, 19 and 21, to z-scores using this relation over here. So let's do that. In the first instance, we have 19 minus 20 over 2 divided by 5. Why? Where do I get 2 and 5? Remember, we've got a variance of 4, therefore a standard deviation of 2, and we've got n, sample size 25, and the square root of 25 is 5. And on the other limit, we've got 21 minus 20 over 2 over 5. Simplifying, we have minus 5 over 2 and plus 5 over 2. Now, when we look up this probability in the Z table, again, we have to be careful because we notice that there are negative values in this in the left limit, and we have to break up this probability into two separate probabilities at the point of 0. However, given that the limits are in absolute values identical, we can merely say that this equals, and given we can exploit the fact that the Z table is a symmetric distribution, and we can say that this equals 2 times the probability that Z lies between 0 and 5 over 2. So all we need to do is look up the probability that Z lies between 0 and 5 over 2, and then multiply that by 2, and we have our solution. In terms of that value is given by 0.4938. So multiply that by 2, and we have the probability that X bar lies between 19 and 21. The rest of the problems follow a similar approach. We can quickly just pause on the very last one over here, just to give you a sense of how to think about this graphically. In this instance, we've got probability that X bar is larger than or equal to 21. Transforming that to a Z-score again results in the probability that X bar is larger than or equal to 5 over 2. What that looks like graphically is as follows. We've got 5 over 2, well, probably about here, 5 over 2. And what you want to determine, what this problem requires you to determine, is the area given over here. Right? Probability that X bar is larger than or equal to 5 over 2. In other words, take on, what is the probability that it takes on a value 5 over 2 or greater? So, how do we approach this one? Well, again, the Z table gives you values from 0 all the way to infinity, and in fact, the probability that X bar lies between 0 and infinity is 0.5. So you can just write that down, and then you can subtract from that the probability that X bar lies between 0, well, in this case, that's the Z transformation, lies between 0 and 5 over 2. And that would give you the solution. In other words, you're subtracting this area over here, straight line shaded area, from the entire half of distribution to find this value over here. And that's how you solve that one.